Determine the first derivative using logarithmic differentiation. So notice, even though the directions specifically tell you to use logarithmic differentiation, if you were to look at this equation, you would need to know that logarithmic differentiation would be required because you have a variable in the base and you also have a variable in the exponent. So that means you cannot use the power rule and you cannot use the derivative rule for exponential functions either. Because there's a variable in both the base and the exponent, logarithmic differentiation is really your only option. So we'll start logarithmic differentiation by taking the natural log of both sides. So we're going to take the natural log of everything on the right and everything on the left. So natural log of y is equal to the natural log of tangent of x raised to the square root of x power. Now the reason we're using logarithmic differentiation, specifically logarithms, is because we can use properties of logs on the right-hand side to basically make the right-hand side look a little bit more simple. So in this case, we have the power rule for logarithms, which lets us take the exponent. So in this case, we have that tangent of x is raised to the square root of x power. And we can bring that out in front and rewrite that with multiplication. So natural log of y will equal the square root of x multiplied by the natural log of tangent of x. And you want to keep using your properties of logarithms as much as you possibly can to rewrite the right-hand side of the equation. In this case, though, we're done. There's nothing else we could do to this natural log of tangent x. No property can be applied here. So now we're ready to do the calculus. And the calculus part is taking the derivative of both sides with respect to x. So I'm showing that we're taking the derivative of everything on the right and everything on the left. That'll be the derivative of natural log of y and the derivative of the square root of x multiplied by the natural log of tangent of x. So the derivative of natural log of y will be 1 over y, and then we have to chain on the derivative of y with respect to x. And then before you jump too deep into the right-hand side, pay close attention that you have multiplication here. This square root of x is getting multiplied by the natural log of tangent of x. So this is another one where we're going to have to utilize our product rule. The first times the derivative of the second plus the second times the derivative of the first. So by first and second, I'm treating the square root of x as my first, my f, and then natural log of tangent of x as my g. So now we'll do our product rule. So the first factor, the f, is the square root of x, and then we have to multiply that by the derivative of natural log of tangent of x. Now be careful, because natural log of tangent of x is a composite function, so we need to remember the chain rule. So the derivative of natural log of tangent of x would be 1 over the tangent of x, and then we have to multiply by the derivative of tangent of x, which is secant squared of x. So again, this is my f, and then this entire thing here is my g prime. Then we're going to add that to our second factor, the g factor, which is the natural log of tangent of x, and that gets multiplied. This is my g, and I'm multiplying it by the derivative of f. But remember that the square root of x can be rewritten as x to the 1/2 power, so the power rule will give us 1/2 x to the negative 1/2 for the derivative. So this is my f prime. So that's my product rule there. Now at this point, I like to do some simplifying or some rewriting on the right-hand side just to make it look a little bit cleaner. So I'm going to just rewrite this as square root of x times secant squared of x divided by tangent of x. And now you could certainly do some trig identities here. I'm not going to bother with that, but you could certainly rewrite secant squared or rewrite tangent of x. And then we're going to have plus the natural log of tangent of x divided by 2 times the square root of x. And remember, that happened because we had a negative exponent, which then pushed the x to the negative 1/2 power into the denominator. We're almost done. Now we want to solve for dy dx. So we're going to multiply both sides by y. So this entire right-hand side, that whole thing, and all of its beauty gets multiplied by y. So we'll have dy dx equals this giant quantity here times y. Now, we don't really want to have our final answer be in terms of both x and y. We want our final answer to be just in terms of x. So that's why our final step here will be to substitute, and let's get rid of this y and go back to the original problem that we were given. And remember, y was equal to tangent of x raised to the square root of x power. So then we'll just plug that back in down here in our derivative. So this is going to be multiplied by the tangent of x raised to the square root of x power. And this lovely answer is our derivative using logarithmic differentiation.